All right, so what we're going to start looking at in Chapter 4 are discrete random variables. So what we're going to first do is we're first going to try to look at to see what a random variable is. And after we understand what a random variable is, we're going to try to understand what kinds of different random variables that we can have. And as we can see, one of those types of random variables that we're going to be able to have are going to be discrete random variables. So then we're going to see what does it mean to be a discrete random variable. And if it's not a discrete random variable, what else is it? And then we'll talk about those just very briefly as well. But more so starting in Chapter 5. So a random variable is simply just some numerical quantity that is generated from a random experiment. That's a definition that your textbook gives you, or the textbook that accompanies this course gives you, is that it's a numerical quantity that's generated from some random experiment. I don't 100% agree with this definition for a random variable, because a random variable technically does not need to be a numerical quantity, but you can translate all random variables to numerical quantities. But this is the definition that your textbook gives you. So it's simply just, we'll go with the definition of the textbook, because that's the one that we're going to primarily be using in this class. And that is that a random variable is some numerical quantity that's generated from some random experiment. So again, you can imagine this random experiment rolling a die, right? Where if you roll a die, obviously you're going to get some number that lands face up, or picking numbers out of a hat or a bag or something like that. Those are all random experiments. You don't know the outcome of the experiment before you conduct it, and it's going to generate some kind of numerical quantity. So then what does it mean to be a discrete random variable? A random variable is called discrete if it has either a finite or a countable number of values. And a random variable is called continuous if its possible values contain a whole interval of numbers. So let's take a step back and let's try to actually figure out what the heck does this mean. What does it mean for it to be a discrete random variable if it either has a finite or a countable number of possible values? So let's do this. If I ask you how many people are passengers in a vehicle, right? You're going to be able to count how many people are in that vehicle, and it's also going to be a finite number, right? Just to make sure everybody's on the same page, what does it mean to be a finite number? It has an end, right? It's not infinite. It doesn't go on forever, right? That it has a finite number, so it's like the number 5 or the number 10. You're not going to have an infinite number of people in a car, right? Like that would be a giant number's car. Just be impossible, right? So we're going to have discrete random variables. They need to be finite, and they need to be countable. Or they need to be finite, or they need to be countable. So it's really, really, really important that it's finite or countable. And there is a very, very big difference. Can you have a number that is countable, but it's infinite? So pi keeps on going on forever and ever and ever, right? It's an irrational number, right? But it is finite, meaning that it doesn't ever go to the number 4, right? So it has an infinite number of decimal places, so that's correct. But it doesn't keep on, like, pi doesn't go on to 10, and then 20, and then 30, and then 3,000, and then 3 million. It doesn't keep on going on forever and ever and ever, right? So technically, pi is a finite number, but it's an irrational number. It just keeps on going on forever and ever. Great question. So let me ask it again. Can you have a countable number that's infinite? So the answer to that is yes, right? You can technically have a countable number that's infinite, right? Think about it like this. Let's say that you just started counting, right? And you went in, you said 1, 2, 3, 4, and then you just started sitting down and got to 1,000 and 1,001, 1,002, 1,003. And then we get out in class, but you still sit here and you keep counting, right? And then the next class comes in and somebody goes, what the heck are you doing? And you're just like, leave me alone, I'm counting, right? And then you get to 10,000, 10,001, 10,002. right? You could technically keep on going on forever and ever and ever. Just keep on counting on forever and ever and ever, right? Assuming that you just keep living on forever and ever and ever. You could keep counting. So technically speaking, there is that counting numbers, you can go all the way to infinity or infinity and beyond, right? Does that make sense? So technically speaking, you could count forever and ever and ever. So what does it mean to be a countable number? A countable number simply just means this. You can arrange numbers from the smallest to the largest, and you can start counting how many that there are, right? For example, here, the number of students in this class is countable, right? You can go and you can say, hey, I'm going to somehow arrange all of you, and then I'm going to count how many that there are. In this building, there's a countable number of students. You can somehow arrange them and say, you're the first, you're the second, you're the third, you're the fourth, right? Everybody get that? So it doesn't matter how big that group is. If you can somehow arrange them from smallest to largest, then you can start counting how many that there are, right? Let's try to distinguish that between a whole interval of numbers. So let me draw that, right? Let's say that we have the interval from 0 to 1. Let me first ask you this. How many numbers are in this interval? How many numbers are between the numbers 0 and 1? No, there's any numbers. I think I heard it. It's an infinite number of numbers, right? So there's an infinite number of numbers between 0 and 1, right? Does everybody agree with that? You could have 0.5, you could have 0.55, you could have 0.555. You could have, if you just keep on going farther and farther and farther down into the decimal places, you can have an infinite number of numbers, right? Does that make sense? Let me ask you this. Are these numbers countable? Can you say, you're the first number, you're the second number, you're the third number, you're the fourth number? Are the numbers in the interval between 0 and 1, are they countable? Yeah. I hear some people say yes, I hear some people say no. All right, so let's try to do it, right? If we wanted to start counting these numbers, and we wanted to say, you're the first number, you're the second number, you're the third number, and so on and so forth, then I think everybody will agree that 0 is going to be our first number. That's where that interval begins, right? But now let's just say, all right, let's say that I say the second number is the number 0.5. But then you would say, hey, wait a second. That shouldn't be the second number because I can find a number that's smaller than 0.5 and that one should come first, right? So maybe you say, no, it should be 0.25. Then somebody else goes, no, I can find a smaller number than that. And that number should come first. So maybe that person comes up with a number 0.1. Then somebody else goes, wait, there's another number that comes before that. It should be 0.01, and that should be our second number. You guys get the gist of what I'm doing up here? Can you ever really identify what that second number would be? It's impossible, because what you can do is, you could say, hey, I think it should be 0.01, but then somebody else can go, no, it should be 0.001. Then somebody else can go, no, it should be 0.0001. And keep on going forever and ever and ever like that, right? Does that make sense to everybody? So we most certainly can identify what the first number is, but we'll never be able to say, this number right here, that's our second number. Because we can always just go a little bit farther down to the decimal places. Right? Does that make sense? So here in this interval, there's an infinite number of numbers, but we can never count them. You guys see the difference between having an infinite number of numbers that you can't count, right? If you're just sitting there going 1, 2, 3, 4, 5, 6, 7, and an infinite number of numbers that you cannot count. Right? Everybody see the difference between them? So here in this interval, we have an uncountably infinite number of numbers in this interval. We have an uncountably infinite number of numbers. But whole numbers, for instance, like 1, 2, 3, 4, 5, those are countably infinite. You can definitely say this is the first number, this is the second number, this is the third number. Right? Is everybody good with the difference between countably infinite and uncountably infinite number? All right. So if everybody's good with that, let's go back to our definition of discrete and continuous random variables. A discrete random variable needs to be finite. So there has to be some endpoint, like
5 people in a vehicle, 6 siblings, 2 adults, right? It has to be some finite number. Or it has to at least be countable. So it doesn't have to stop, but you have to at least say, this is the first number, this is the second number, this is the third number, and so on. If one of these 2 conditions apply, we have a discrete random variable. If it's not finite and they're not countable, then we're going to say that it's a continuous random variable because we're going to have an uncountably infinite number of numbers. All right. So what does this really mean? If all of this didn't make a whole lot of sense, the portion that's going to be important to you is this. If we have discrete random variables, you can think about the distribution of that as being like Connect 4, like I said before, right? Where you drop it like these chips down individual shoots, right? So therefore, if we have a distribution for a discrete random variable, like this right here would be a perfect example for that discrete random variable. It's just like these different dots, right? If you have a continuous random variable, you don't have individual buckets. You don't have individual buckets that you put them in. You are just going to have some continuous line for this distribution, right? So therefore, the distribution of a discrete random variable looks like something like Connect 4. But the distribution for a continuous random variable is going to be some continuous. Does that make sense? All right. So let's try to see if we can identify continuous and discrete random variables. So for each one of these, we're going to say whether or not it's discrete or continuous. Let's start off with A. The number of passengers in a car, discrete or continuous? Discrete. Why is it discrete? It's countable and it's finite, right? You can count how many people are in a car, and you can also know that there's going to be a finite number in there. What about the number of clerical errors on a Word document? So this would be like spelling errors or something. It's discrete. Why is it discrete? Right, exactly. Like you can spell check it, find out a certain amount of errors. Doesn't matter if you have the worst secretary in the world, right? There's still going to be a finite number of mistakes on there, and you can count how many that there are. So it's discrete. Good. What about the weight of a baby giraffe? Continuous. Who thinks it's continuous? Who thinks it's discrete? Who's not 100% sure? All right, cool. So let's go through this one, right? Let's say I have a baby giraffe, right? And I'm like, yeah, sweet, I have a baby giraffe, right? And I'm standing here with this baby giraffe, and for some reason I have this baby giraffe on a leash, right? And I'm like, sweet, I have a baby giraffe. And as I'm standing here with this baby giraffe, I'm like, I wonder how much this thing weighs, right? So then I'm like, I'm going to go put this thing on the scale in my bathroom. So, of course, unbeknownst to my wife, I bring this baby giraffe into our house, and somehow I wrestle this thing up onto like the scale in my house, right? And on this scale it says, I don't know, 365.2 pounds, right? To which I say, that's a big baby, right? So here I am with this 365.2 pound baby giraffe in my bathroom in my house, right? And then I say, and I go, I wonder if it's 365.2, or is it more like 365.19 pounds, right? That sounds like a reasonable thing to ask yourself in that situation. So then I'm like, how am I going to figure that out? I know. I'm going to take this thing to the chemistry lab on campus at UNCC because they have really accurate scales there. So here now I'm wrestling this baby giraffe on the campus, trying to make sure I don't get caught. And I break into the chemistry lab. So it's kind of like turning into like one of those hangover movies, right? And I take this baby giraffe and I somehow get this baby giraffe on this accurate scale. And it's 365.19 pounds, right? And I'm like, cool, now I know it down to 4 decimal places. But then I get to thinking, what if I get a really, really accurate? I could take it to like NASA, right? Put it on one of its scales, and I could keep going on and on and on. What I'm trying to say with all that here is this. How many decimal places I get accuracy isn't dependent on what its weight is. It's just dependent on the accuracy of the scale that I'm using, right? Its weight doesn't change. Its weight is what its weight is. It just depends on how closely can I measure its weight, and that just depends on the accuracy of the scale. Right? Does that make sense to everybody? If you run into a situation like that, chances are you're dealing with a continuous random variable, right? Because you could keep on going on forever and ever and ever if you wanted to, down into the decimal places, and it just depended on the accuracy of the equipment, right? If you try to compare that to maybe like the number of kids that you have, right? If somebody comes up to me and goes, how many kids do you have? I'm not going to be like 2.00000 kids, right? They're going to be like, this dude's crazy, right? Turn around and like walk away, right? Nobody would say that. But if you can keep on going farther down into the decimal places for something like weights, then here chances are we're dealing with a continuous random variable. Now, let me pause here for a second, because as we're going to see, sometimes what a variable is, like there's a little bit of a gray area there, right? What happens if I asked you, what is the weight of a baby giraffe to the closest pound? Well, now going down into the decimal places doesn't make a difference, right? Now you would just say, well, it's 365 pounds. Well, now there, it doesn't matter if I just take it to the scale in my house, or if I take it to the scale at UNCC or to NASA, I'm always going to end up with 365 because the accuracy of my equipment doesn't matter, right? Is everybody good with that? So therefore, the weight of a baby giraffe is a continuous random variable. But if I say the weight of a baby giraffe to the closest pound, then that's going to be a discrete random variable. Right? Does that make sense to everybody? A big confusion that often comes up sometimes is whenever people say, oh, it has to do with decimal places. That's kind of true. It kind of has to do with decimal places. But if I said, what is the weight of a baby giraffe to the closest half pound? Is that going to be discrete or continuous? It's still going to be discrete, right? Because again, as long as I can get to the half pound, I don't need to take this thing to NASA to figure out what my value is, right? I just have to get to the closest half pound. So therefore, decimal places don't necessarily matter, but is everybody good with how looking at the decimal place is going to help you determine if this is a discrete or a continuous random variable? All right. What about the height of an elephant to the nearest inch? Discrete, right? Is everybody good that this is discrete? If I said it was just the height of an elephant, it would be discrete or continuous. Everybody get the gist? Cool. The time between customers entering a checkout lane at a retail store. So you're looking at the time between customers. Continuous. Why is it continuous? Awesome, right? It doesn't matter if I'm doing this thing on, like if I'm standing there counting in seconds, right? Or if, well, here it doesn't matter if I'm standing there counting in seconds, or if I'm using my phone, or if I'm using like a super accurate stopwatch or something like that, right? If I'm just looking at time, I can get as accurate as I want. But then if I said the time between customers at a retail store to the closest second, it would be discrete. Awesome. The number of accident-free days in a month at a factory. Discrete. Because again, it's going to be finite and countable. All right, is everybody good with the difference between discrete and continuous random variables? All right. We've started to talk a little bit already about probability distributions. Let's talk about it one more time. The probability distribution of a discrete random variable x is a list of each possible value of x together with the probability that x takes that value in one trial of an experiment. All right, we've seen this stuff before. Let me briefly jog your memory on this. What we're going to see here down here in a minute is we're going to see that probability distributions are sometimes written in terms of a table, but you can also do it in terms of a graph like we did with Connect 4. But let's just do a really, really quick, easy example so everybody can understand exactly what this definition is saying. Suppose that I roll a 6-sided fair die, right? What is my sample space? 1 through 6, right? So each one of these things are possible outcomes. Now, so each one of these are possible x values, right? Remember that we said in our data set, each individual outcome, that's what we're going to represent by x. These are our possible x values. What the probability distribution is it says, hey, we don't just want to list each possible value of x. That's what we've done so far. But we also want to record the probability that x takes this value. So here, what we're going to write this then is we're going to write the probability of x, right? Remember that P in parentheses means probability of. So we're going to record the probability of x values. And what's the probability of getting a number 1? And then just 1/6 for all of these, right? So this right here would be a perfect example of a probability distribution for the discrete random variable of rolling a 6-sided fair die. We obviously could also do this in terms of the Connect 4 type distribution that we've been talking about. We're going to have 1 number 1, 1 number 2, 1 number 3, 1 number 4, 1 number 5, and 1 number 6. So all of these are going to happen one time. But I don't want to create a frequency distribution. I want to create a relative frequency distribution. So therefore, I'm going to have to write this as 1/6, or it's just a probability. All right, so both of these are perfect examples of probability distributions. The one that we're going to work with mostly in this chapter is going to be the one on the right. Simply just more of a table form. But what we're doing here is we're simply just listing all possible values of x, and then the probability of getting those values of x. And since here we have a 6-sided fair die, we end up with this right here. Everybody good with what a probability distribution is? All right, then let's look at the mean, or it's also called the expected value of a discrete random variable of x. All right, so here, whenever you see this symbol right here, what do you do again? Sum them up. So here, in between x and p of x, this is multiplication. Right? It's just assumed that that has a multiplication symbol in it. So what's going to be the order of operation then for this formula? Multiply first, and then we're going to add them all up, right? So then, well, if we wanted to do it for this example up here, just really quickly, if we wanted to have x times p of x, well then what we're going to do is we're going to multiply this x times its p of x. So we're going to have 1 times 1/6. And then we're going to add that to the other x times its p of x. So 2 times 1/6. And so on and so forth. Everybody get the gist of what I'm doing? I'm going to take each one of these x values, I'm going to multiply it by its p of x, and then I'm going to add them all together. So I'm going to go ... plus 6 times 1/6. Now, whatever that comes out to be, that's going to be the average, or the mean, or the expected value of this discrete random variable x. So what are we doing now differently than we did whenever we calculated out the mean before? Because we've been calculating out means ever since we got done with Chapter 2, right? Whenever we've calculated out means up until now, we always just had a set of numbers, and we added up those numbers and divided by how many that we have to calculate out the average. Right? That's how we've been doing it so far. But what's different now is we're not just adding up 1, 2, 3, 4, 5, and 6 and dividing by 6 to get us that average. But now what we're saying is that there's a probability associated with each one of those numbers. Right? Does that make sense? Let's say it like this. If you want to have a visual depiction of how this expected value is different than the mean that we've been calculating out in Chapter 2, you can think about it like this. Suppose that I had balls in a bag, and I told you to reach into this bag and pull out a ball, right? Whatever ball that is, I don't know, is the prize that you get or something like that. If I had a bunch of small, tiny little pebble-type balls in this bag, but then I also had one really, 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 really huge ball, well, chances are, right, or maybe I had like, 2 huge balls in here, right? And then like a bunch of little pebbles down at the bottom. Well, the chances are that if you're going to reach into this bag and pull out one of the balls, let's just say that it's more likely that you're going to pull out one of the bigger balls, right? You're going to say, like I say, hey, inside these balls is a prize. And there's like these little tiny pebbles down there, but then these are also like these bigger balls. Like imagine like you're back in like a 4-year-old mindset, right? If it was me, I'd like try to take out the big balls because I feel like it's something huge, right? So chances are you're going to pick out one of these things right here. But let's just say it's a farce, right? And then inside the big balls, there's only $1 in here. But inside each one of these little balls, there's like $20 in there, right? But you didn't know that, right? You're just like this 4-year-old kid who's reaching into this bag. So chances are that the expected value of money that you would get, chances are it's just going to be $1. Right? Does that make sense? That the expected value should be closer to $1 than it would be to $20. Does that make sense? So what we're doing here is that we're not just adding up, we're not just finding the arithmetic mean of these individual values, but now we're associating a probability along with getting each one of these individual values as well. All right. So let's try to put this into a little bit more of a different kind of application. Here we're going to say that suppose a fair coin is tossed 3 times. Let X be the number of heads that we observe. What is the sample space for this experiment? First, what is the symbol that we use for the sample space? S, right? And if we're flipping a fair coin 3 times, what is our sample space? Awesome. Right, so we're going to have heads, 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 tails, and then so on and so forth for all the combinations, right? So we're going to have heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. That's going to be our sample space. Does that make sense? Who wants me to go over this one more time? Everybody go with why this is the sample space? It's not just heads or tails, right? We went over this whenever we were flipping the coin twice, right? Now we're just flipping this coin 3 times. So let's think about this, right? Let's make sure that we have 8 possibilities right here. Let's make sure that we first know that we should be getting 8 possibilities. On the first flip of the coin, you can either get heads or tails. Does that make sense, everybody? Let me draw this a little bit differently. Give myself a little bit more space. On the first flip of the coin, you can either get heads or tails. So let's say we'll go in one direction or the other. But then here, if we flip a coin the second time, so we'll be at these spots. If we flip a coin a second time, if we got heads the first flip, then on our second flip, we can also get heads and tails. But if we got tails the first time, on our second flip, we can also get heads or tails. Everybody good with what I'm doing up here? Then, here, this represents where we are after our second flip. So then, after our second flip, we can either get heads or tails again, regardless of what we got on our first or second flip. tails, heads is right here. Everybody good with this? So therefore, now at this very end right here, this is where we're going to stop. So we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes that we can get. And then you could just follow these things along, right? Here we're getting tails, heads, heads. And here we have tails, heads, heads. Here we're getting tails, tails, tails. We're getting tails, tails, tails. You can just go through this tree and figure out what all your possible outcomes are. Does that make sense, everybody? All right, so we know we have 8 possible outcomes. Here's our sample space for the experiment. What is the probability distribution for this experiment? Great question, right? Great suggestion, right? It's not quite right, and here's why. Let's go back to what we had up here. We said that this right here was our probability distribution for rolling that 6-sided fair die, right? In our probability distribution, we're always going to list our discrete random variable x and the probability that's associated with that x value, right? So we're going to try to do the same thing right here. We're going to try to list our possible x values and also the probability associated with those x values. So let me ask you this. What are our x values? How do we define our x values here? I think I heard it. Whoever said that, to say it loud. Heads. Heads, right? It says right here, let x be the number of heads observed. Right? Is everybody good with that? So the way that we're defining what our x values are how many heads we've observed. Right? Is everybody good with that? So here we have our sample space for our experiment. These are the possible outcomes. But what we're doing is now we're going to define x as being the number of heads that we observe. So how many heads could we observe? It's not 1 through 3. You're close. Not 1 through 4. Can't get 4 heads if we only flip the coin 3 times. So we can definitely get 1 heads. It'd be 0 through 3, right? There's also a possibility where we get no heads, so it's going to be 0 through 3. All right, is everybody good with this so far? So, let's continue with this, and then I'm going to say something else about part A here in a second. Is everybody good with the fact that if we're defining our random variable x to be the number of heads that we get if we flip a fair coin 3 times, then the number of heads that we could get are 0 heads, we could get 1 heads, 2 heads, or 3 heads. Right? Is everybody good with this? All right. So now what we want to do is in our probability distribution table, we want to also record the probability with which these x values occur. So what's the probability that we're going to get 0 heads? 1 out of 8. The only time in here where we get 0 heads is just this one time right here out of a total of 8 possibilities. So therefore, the probability with which we would get 0 heads is just 1 out of 8. Does that make sense? What's the probability that we would get 1 heads? So let's see. Here we're going to get 1 heads. Here we're going to get 1 heads. What am I missing? Oh, thanks. And here we're going to get 1 heads. So therefore, we have 3 out of the 8 possibilities. What's the probability with which we're going to get 2 heads? Again, 3 out of 8. I'll circle them this time. Here's 1 of them. Here's 2 of them. And then here's 3 of them. And then what's the probability with which we're going to get 3 heads? 1 out of 8. Right, we could either go through here, or again, we could just add up these and subtract them from 1 and get the probability. Is everybody good with this probability distribution table? All right. So, like I said, let me also backtrack now to our sample space up here. Because one of the things that we could do is we could say that, hey, these are all the possible outcomes of us flipping a fair coin 3 times, right? Or really just flipping any coin 3 times. These are the possible outcomes that we could get. It doesn't even have to be a fair coin. Since we're coming down here and we're starting to look at our x values to be the number of heads that we can get, what we could also do is we could also define our sample space to be 0, 1, 2, or 3. As long as we're saying that each one of those things in our sample space represents a random variable x. So then here, this would be our sample space for the outcomes of flipping a coin 3 times. But this right here would be our sample space for our random variable x. Everybody good with this? All right. So now we want to figure out for C, what is the expected value of x? How would we figure out what the expected value is of x? The x times its probability. So we're going to take all of our x values and multiply it by its probability. So we're going to have 0 times 1/8, 1 times 3/8, 2 times 3/8, and then 3 times 1/8. And after we multiply each x value times its probability, what do? Add them up. So then this is going to be mu, or the expected value of x, just like we have up here. And if you do this arithmetic, I'll save you the arithmetic, this comes out to 1.5. So then the expected value that you would get is 1.5. What does that mean? What does it mean to have an expected value of 1.5?
So x is the number of heads observed. You're trying to say that heads will come up 1.5 times?
Yeah, exactly. Right? Think about it like this. If I say, hey, we're going to flip a fair coin, and I'm going to flip this fair coin twice, right? How many heads would you expect?
Just flip it twice or 3?
Flip it twice. How many heads would you expect? Just 1.
Yeah.
Right? Does that make sense? If I flipped a fair coin 4 times, how many heads would you expect? 2. Right? So if I flip it twice, I get 1. If I flip it 4 times, I get 2. So if I flip a fair coin 3 times, I would expect half of them to be heads, right? So therefore, half of the flips is just 1.5 times, right? So 1.5 heads doesn't make like intuitive sense. But if we don't flip a fair coin 3 times, if we flip a fair coin 30 times, how many heads would you expect? 15, or just 10 times whatever we got right here, right? Now does this make sense what this 1.5 means? It means that if you flip a fair coin 3 times, you're expecting half of them to be heads, and half of 3 times is just 1.5. Just that the numbers are a little bit silly in this problem. All right, does that make sense? All right, how do you guys feel about this example? All right, let's go on then to the next page of the notes. Page in the notes is this. All right, so here we're talking about the variance of a continuous random variable, of a discrete random variable x is one of these 2 formulas. And if if I remember right, I think that these are on your formula sheet. Can anybody look at your formula sheet and verify that? I do have one. Yep, so these are on your formula sheet. So what we have right here, so let me take a look at these notes here real quick. This is a little crooked. How can I fix this? Here we go. For the variance of a discrete random variable, we have these two possible formulas. And then for the standard deviation of a discrete random variable, we have these two formulas. But just like we had before, what's the difference between variance and a standard deviation? One is squared, right? So this one right here is squared. This one right here is not squared. So then the only difference between these two formulas is one of them has a square root and the other one doesn't. Does that make sense? So if you look on your formula sheet, you're given the definition for which one? What is this? Standard deviation. So this one has the square root on it. So if you wanted to know the formula for the variance of a discrete random variable, what would you do to these formulas?
Square root.
Not square root it. Square it, right? You just want to get rid of the square root, so we would just square these right here. Right, does that make sense to everybody? So I said that you had this formula on your formula sheet. Technically, you have that of the standard deviation, but I think everybody's good with how to get the formula for variance from these two formulas right here. All right. So,
You're going to have access to the formula sheet on your test, like I said.
so let's try to see if we can apply that stuff to this next problem down here. It says that in the following table, X represents the number of long-distance telephone calls made during a 1-hour period in a telemarketing department. The probability distribution of X is shown in the following table. And here you have that table. Now it's asking you to find the probability that 2 is less than or equal to X, and that's strictly less than 5.
All right. So let me just ask you this, right? Without trying to find the probability of this, if I asked you for a whole number, and I said, hey, I'm looking for the whole numbers that are greater than or equal to 2, but strictly less than 5, what numbers are those? 2, 3, and 4. 2, 3, and 4, right? Is everybody good that we're looking at the numbers 2, 3, and 4?
So now we're just looking at the numbers 2, 3, and 4, because that's greater than or equal to 2, but strictly less than 5. But now what I'm asking you to do is to find the probability of those. So what would you do? You just add them up, right? That's how you find the probability of an event, is you add up the probabilities of all the outcomes in that event. So therefore, this is just the same thing as the probability of 2 plus the probability of 3 plus the probability of 4. And we know that this is 0.14 plus 0.31 plus 0.33. And this comes out to what? 0.78. Awesome. So then the probability that X takes the values 2, 3, or 4 is going to be 78%. 0.78. Any questions about this first one? You guys are definitely going to have to do a problem like this on your homework and also on the second exam. Any questions about this whatsoever? All right, the next thing we want to do is find the mean of the random variable. Take a minute or two for yourself and see if you can calculate out the mean of this discrete random variable X. Anybody need a little extra time? All right. So if we wanted to find the mean of this discrete random variable, what are we going to do?
2x times p of x plus and so forth.
Awesome. So we're going to multiply all of these together, each x times its p of x, and then we're going to add them to each other. So we're going to try to find the mean, which is the same thing as the expected value of our discrete random variable x. And for that, we're going to have 1 times 0.03 plus 2 times 0.14 plus 3 times 0.31. Is everybody good with what I'm doing up here? Plus 4 times 0.33 plus 5 times 0.15 plus 6 times 0.04. And if you do this arithmetic, what do you end up with? 3.7? 3.55? Everybody good with 3.55? How you guys feel about finding the mean or the expected value of a discrete random variable? Everybody good with this? All right, then take a minute or so for yourself, or 2 minutes or so, and see if you can find the standard deviation of this discrete random variable x. Here, I'll move it down so you guys can also see the formula for it. Does anybody need a little extra time? All right, let's do this one again. All right, if we want to do a standard deviation of a discrete random variable x, we can either use one of these two formulas. I'll call this formula number 1, and I'll call this formula number 2. we're going to do both of them just depending on, just to make sure that if you used one or the other one that you know how to apply the formula. But we'll start off with the first one. So we're trying to find the standard deviation of the discrete random variable. I'm going to copy down this formula that we have above. All right. Now, if we want to do this, what's the order of operation in this formula? What are we going to do first? We're going to do the parentheses, and then after we do this parenthesis, what are we going to do? Square it, and then multiply it, and then? Yeah, so first we're going to add them all up, and then we're going to take the square root of all of them, right? So what we're saying here is this. We're going to take our first x value, and what's our first x value? 1. We're going to subtract mu from it. What's mu equal to? 3.55. That's what we just figured out in our previous part of this problem. Then we're going to square this. And then we're going to multiply this by its p of x. And what is the p of x? 0.03, right? Because here the p value, or the probability associated with that x value is 0.03. So now we've done all of this right here, so then we're going to add that to the next x value, and the next x value is the number 2. We're going to subtract the mean from that, which is 3.55. We're going to square this, and then we're going to multiply it to its probability, 0.14. All right, is everybody good with what I'm doing up here? Then I'm going to take the third x value, subtract the mean from it, square it, and multiply it by its probability, plus the fourth x value minus the mean, square it, times its probability. Fifth x value minus the mean, square root, times its probability. And then the sixth x value minus the mean, square root, and by its probability. Am I done here? What do I still have to do? Add them all up, but what am I still missing here? Square root. I have to square root all of these things, right? Everybody good with this? So then after I do all of this, I still have to square root the entire thing. And if you do this arithmetic, what you guys get? Anybody get a number? 1.1? Anybody else get 1.1? Anybody else get anything? Nobody else got that far? You got the same thing? 1.1? Alright, cool. So, obviously finding the standard deviation of a discrete random variable by hand is quite tedious, right? Doing all this arithmetic, especially if you have to do something like this on a test. If you have like 3 problems like this on a test, like those 3 problems are going to take forever, right? This is one of the things where it's extremely beneficial to have like a TI-83 or a TI-84, or one of the pluses, the TI-83 plus or TI-84 plus, because those calculators have built-in functions in them, where the only thing that you're really going to have to do is you're going to have to put these values into the calculator, and then you're going to say, give me the standard deviation for the discrete random variable, and then it's going to spit this number out for you. Right? So if you know how to do it on your calculator, a problem like this is going to probably take you something like 30 seconds to do. And if you do it by hand, it's obviously going to take you, 2 or 3 minutes to do it.
How do you do that on a calculator?
On Canvas, I posted like a calculator cheat sheet.
Okay,
And
cool.
on there, there's a step-by-step guide of how to do it. I believe that the calculator cheat sheet was made for a TI-83 or 84, one of those two.
Okay.
But the buttons are very, very similar for those two calculators. It's going to be a little bit different if you have a Casio or something like that, like one of the other brands. But if you have a TI calculator, the cheat sheet should help you out a lot.
Yeah, for real. Thank you.
Sure. Yep, or YouTube, YouTube University, right? Like, I love YouTube. You figure out how to change oil on your car, go to YouTube, right? Need to figure out anything, just go to YouTube. Like, there's so many things on YouTube, right? Like, craziness. Exactly, right?
I'm fixing a dent in my car today with the plunger. I learned it from YouTube.
From YouTube, right? Like, YouTube is so helpful. So extremely helpful. Sometimes I wonder why I went to school. I could have probably learned all the stuff that I needed to just going on the YouTube. Pretty much, right? See? Exactly. Yeah, and it's just like, hey, there's so much random stuff on there too. Like, anytime I had questions about stuff, you just go to YouTube and you're good to go. Not all of them are good, right? Like some of them, you have to like listen to somebody's life story first before you can, figure out how to do anything.
That's when I go forward to like I think they're saying something for it, and then I'll stop and go, oh, never mind.
Yeah. But there's some pretty neat stuff that they have on there. Stuff that you would like never think about. We never used that other formula. Does anybody? Well, let's just do that other formula here real quick. I want to show you guys at least once how to apply the second formula. I know that most of you are going to probably now go to YouTube or go to Canvas and look at that cheat sheet, but I want to show it at least once.
So on the test, the only thing we're turning in is the sample sheet?
So you're going to turn everything in. You're going to
Okay.
turn in the test and your scratch paper and everything, but the only thing I'm going to grade is the bubble sheet.
Okay, so you're not looking for work. Okay.
I don't care, right? You can. I don't care how you get the answers as long as you're not somehow copying them from your neighbor or somehow cheating to get them. I really don't care, right?
Okay.
It's multiple choice. If you guess and you get it right, good for you, right? If you know how to do it or however you're getting the correct answer, completely fine. All right, so let's look at that second formula. Second formula for calculating out the standard deviation. This is our second formula. Is the square root of sum of x squared times p of x, and then this quantity minus mu squared. So in this formula, what's our order of operation?
Brackets.
We're going to do what's in the brackets first. And when we're in the brackets, what do we do first? We're going to square, and then after we square, we're going to do what? Multiply to the p of x, and then we're going to add all those together. Right? All right. So the way that this would look is this. What is our first x value? 1. So then we're going to have 1, but we're going to square it. And then we're going to multiply that to its p of x. And what's its p of x? Cool. And then that's this stuff right here. And now we're going to add it to the same thing for the next x value. So the next x value is 2. We're going to square it, multiply it towards to its p of x. Then 3 squared times 0.31. Everybody good with what I'm doing up here? Then plus 4 squared times 0.33 plus 5 squared times 0.15 plus 6 squared times 0.04. Alright, so now I did all that stuff. I'm going to close my bracket. Right, so I did everything inside the brackets now. Now I still have to subtract mu squared. So then from all of this, I'm going to subtract mu squared. And mu is equal to what? 3.55. So I'm going to subtract 3.55 squared. And what do I still have to do? Square root it. All right, is everybody good with this? Now, if you do this arithmetic, I didn't verify the 1.1 from the previous example or previous page. But if 1.1 was the correct answer for the previous one, then 1.1 should be the correct answer. All right, how do you guys feel about reading and applying those formulas? Who's good with reading and applying the formulas? All right. Awesome. Then let's go on into another example. take 3 minutes or so for yourself and see if you can do A and B. Does anybody need a little extra time? Everybody's good? All right. So for A, we're trying to find the probability that 2 is strictly greater than x, which is strictly less than 5. what numbers fall into that range?
2, 3, 4, 5.
So it's just 3 and 4, right? Because 2 is equal. So here, if we're looking for x being strictly greater than 2, then if x is strictly greater than 2, then it can be 3, but it cannot be 2. And if we're looking for x to be strictly less than 5, then it cannot be 5. So then it can be at most 4. So it's only going to be the numbers 3 and 4. All right, is everybody good with the numbers just being 3 and 4? All right. So then here what we're going to do is, then this is going to be equal to the probability that x is equal to 3 plus the probability that x is equal to 4. And then here we're going to have 0.28 plus 0.20, which is equal to 0.48. Is everybody good with A? Any questions whatsoever about A? All right, then we're trying to figure out the mean score or the expected value of x. How do we figure out the expected value or the mean score? All the others, right? Cool, awesome. So we're trying to find the mean, which is the expected value of x. In order to find that, we're going to take these x's and multiply them by their p of x, and then add them together. So we're going to have 1 times 0.16 plus 2 times 0.22 plus 3 times 0.28. Is everybody good with this, what I'm doing up here? Plus 4 times 0.20 plus 5 times 0.14. And if you do this arithmetic, what you guys end up with? 2.94. Anybody else also get 2.94? Cool, 2.94 it is. How do you guys feel about A and B? All right, then what we're going to do is we're not going to do C today. And what I'm going to ask you to do is to go to Canvas, look at that calculator cheat sheet on Canvas, figure out how to use your calculator to calculate out a question like C. And before you guys come to class tomorrow, everybody should be completely comfortable with how to calculate out the standard deviation or the variance of a discrete random variable using a calculator. So much so that I might be giving you guys some numbers and giving you guys like 60 seconds to take like a pop quiz, right? So everybody should feel completely comfortable with how to calculate something like this on the calculator before tomorrow. Again, if you don't have a calculator, you can take your ID up to the math department and you can check out a calculator. All right, any questions about any of that stuff? Then I will see you guys tomorrow.
Are these nuts just trash? Or are we going to use them?
Those are the wrong ones. So
Okay.
use those trash ones.
Okay.
Yeah, I posted the wrong ones. I also posted the right ones to